Thanks, Matt.
Yeah.
Good thinking.
Yeah, thank you for this. So we started recording this meeting. We are going to give a very high overview of Plenum and Node and just go through the diagrams that we already have. And at least I will point to the documentation, architecture, and technical documentation that we have, so that you can continue learning it by ourselves. And of course, if anyone has any questions, concerns, or any help in understanding, we will be happy to have more meetings and discuss it in more details. Okay, so first of all, the main source, the main index of any documentation for Plenum and Node is README. So if you want, and actually it has almost all the links that are needed if you want to understand Plenum, Node, how to work with the code, how to set up your dev environment, and so on. Please feel free to extend it if you see any inconsistency or you edit, I know, new helper script you want to mention that can help people. So any help here is appreciated. So if you have a look at the Plenum README, it has links to our existing documentations. It has a link to RBFT paper, because this is the very core, this is the heart of Plenum, the consensus protocol that is implemented in Plenum. And of course, this paper must be read by everyone who wants to contribute to Plenum code. So it also has a description of what is repository structure, what it contains, as well as dependencies, and links on how to contribute, how to send a pull requests, and so on. So in particular, the Plenum consists of the Plenum package, Plenum module. This is a consensus protocol implemented on base of RBFT. Also, it has a ledger. So this is a transaction log and Merkle tree implementation. It has a state based on Patricia tree. It has secure transport abstraction based on ZeroMQ. And it has some other helper methods and abstractions. So Plenum uses Lipsodium as for crypto stuff, and also Indy Crypto, which is also based on Lipsodium. And it uses ZeroMQ as secure transport and KRCP as a protocol for this communication. One moment, sorry. Okay, so in the node, it also has a README, and it also has a description of this repository, dependent projects, and so on. In the node also has a development setup. This is a guideline and scripts which can help you to start developing, because Plenum and Node are now officially work only on Ubuntu 16. So yeah, it has some setups on how to install all required dependencies and how to configure your PyCharm and so on. And the quick setup scripts can also be found in Indy Node. So in general, Indy Node and Indy Plenum contains all the main functionality related to consensus, to the ledger, to the state. And Indy Node is supposed to be a thin extension with identity-specific, custom-specific transactions, such as schema, claim def, and so on. Also, Indy Node contains the logic related to upgrade. Unfortunately, the separation is not so clean. The API is not so clean between Plenum and Node. So in some places, coupled. So you need to take it into account. And sometimes checks may be affected, maybe needed in both Plenum and Node. But usually, if you work on consensus issues, on ledger issues, you do it in Plenum. But if you work on something related to schema, claim def, to real transactions implementations and upgrade, you do it only in Indy node. Okay, so in Plenum, in addition to README, in Plenum node, there is a docs folder. You can also learn and investigate it, and it has a number of different documents. Documents in Indy node, in particular, they contain a format for all our transactions, for all our requests. You can see so it has a common structure of transaction, common structure of request, specification of every attribute, and so on. And again, if you see any type or any consistency, feel free to send a pull request to fix it. It has also description of upgrade, for example, some other diagrams, and so on. Documentation in Indy Plenum, it's more basic because it has a description and architecture principles of consensus protocol of what is Plenum actually is, what is ledger, and so on. And I suggest to go in more details, have a look at Plenum and have a look at these documents in particular. So there is a main .md here. So you can see the overview of the system. So what is Plenum, what is Indy node? So Plenum and Indy node is a system that allows you to have a replicated state, replicated ordered log of transactions that we call the ledger. So we're making sure that every node in the system has the same transactions and in the same order. And all validator nodes participate in decision on what is this order. How the nodes decide this? Because every node runs a consensus protocol based on RBFT to agree on this order. So usually consensus protocol, the main goal of this protocol is to answer the question, what is the order of transactions, how to execute and how to apply them. So as you know, we have several ledgers. We have three main ledgers: domain, pool, and config, every with separate purposes. Apart from ledger, we have a state based on a Merkle-Patricia tree, and it can be considered as a projection of the ledger aggregating the current state. So an example that a user may rotate his key, and every key rotation is a separate transaction on the ledger. But usually you need to know what is the current state, what is the current key for this DID. And the state can help you in answering this question, can get the aggregated key, the current key value. Moreover, the Patricia Merkle tree allows you to go to the past and get the value of the key for a particular period of time. So it's also implemented and used, for example, in revocation. There is a storages document, and you can have a look and get more details about what ledgers we have, what states we have, and actually of what databases, what caches, and auxiliary databases we have. Okay, so you know that clients communicate with the node also using ZeroMQ, ZeroMQ, as well as node-to-node communication. So as of now, we use it for both, but you may hear that the plans are to get rid of ZeroMQ for client, at least for client-to-node communication, and move to something like agent-to-agent. But as of now, it's basically the same protocol. Okay, so usually only the clients with specific permissions can send write requests to the ledger because we require signature. We usually require the DID needs to be present on the ledger to have the signature. But read requests to the ledger, they don't require any signatures, so anyone can read from the ledger. That's why our blockchain is public permissioned. Okay, so we're going in more details when we'll discuss a consensus diagram on what phases we have in our protocol what is propagation, and so on. Important parts of the system is catch-up, because during the life of the system, during the workflow, some nodes may be behind. It can be just because this is a new node that just joined the system, or it can be because the node was disconnected for some time, or by any reasons, and the node need to catch up missing transactions. So we have a protocol, we have a process for this, which is called catch-up process. Moreover, new clients, especially when connecting to the pool, they also perform a catch-up to get the up-to-date state of the pool, of the nodes they need to connect to. Because the configuration of the network, it's also part of the blockchain, part of the ledger. We have a specific ledger called pool ledger, and it contains only the transactions related to configuration of the pool. And the clients, they need to catch up only the pool ledger, not domain, not config. Okay, so the next important thing is that if the protocol realizes that some required messages are absent, they can use a concept of message requests to get these missing messages from other nodes. So it can be used for missing propagate messages or for missing preprepares and so on. Okay, so very important thing is a view change process. So of course, according to all BFT-based PBFT-based protocols, the primary who actually suggests the order of transactions needs to be changed from time to time. It can be changed just because it behaves maliciously, or because it degrades performance, or because of some other reasons. And the process of changing who is the current primary is called view change. It's called the view change. So during the view change, the pool selects a new leader. As of now, it's just a round robin. So the next node in the list is selected, active node. And the current protocol is kind of a custom one based on catch-up and prepared certificate. And one of the big epics that we have is to implement view change as described in PBFT, because it's actually how RBFT should work. Okay, so this is a very brief overview. And now you can see that in the docs, we have a new folder, which is called diagrams. And as of now, we have the diagrams for consensus protocol. We have diagrams for catch-up procedure. We have diagrams for read and write requests from both client and node point of view. And we have diagrams with storages. So let's start with consensus protocol, because this is, I think, the main one. Okay, so very important thing that Plenum is not a pure implementation of RBFT. It implements RBFT with some improvements, and I think it's very important to understand how Plenum deviates from RBFT. So in RBFT paper, I mean, it deals with just a single request being ordered. But in Plenum, we have a concept of three phase commit batches, 3VC batches. So we have this improvement to order the whole batch of transactions. So it can be like 100 or even 1,000 of transactions ordered at the same time. That's why we have better performance than it just if we ordered only a single transaction every time. Because you know the protocol is very chatty. It requires a lot of messages. You can see it later on this diagram to order a single request. So it's much more efficient to do it in batches. This is the first specific. The second specific. Usually, in theory, all PBFT-based papers, they're dealing only with ordering of requests. So we have a request. The consensus protocol decides what is the order of this transaction, of this request, and then the execution of request is out of scope. It's assumed to be done after ordering. But Plenum, not only Plenum, but some other implementations of PBFT-like protocols. In Plenum, the consensus and validation and applying of transactions of requests is combined. So during consensus, we are not only decide what is the order of requests, we at the same time apply the requests, the three-phase commit batch of requests to our ledger and state, and do all necessary verification and validation. Why it's done like this? Because first of all, it allows to have always a consistent state, because during consensus we can check that all nodes have consistent data. Because, well, if it's not consistent, if root hashes are not equal, then we can immediately notice this, and these transactions will not be ordered. Also, it allows us to have to not have invalid transactions on the ledger. Because if we did validation only after it's ordered, then it means that all incorrect transactions should probably be on the ledger, and it can be quite a lot of spam and garbage. So this is important specific, that in Plenum, consensus is combined with validation and applying of requests. Third specific is that Plenum also has a concept of time, because every transaction, so the pool agrees upon what is the time for every transaction, for every batch of transaction. And this time is very critical for freshness. Because later on the clients can get the time on when transaction was ordered, when the state was refreshed, was updated, and can decide based on this time whether the result from the pool is fresh enough for them. So this is also quite important for real use cases for applications, because the freshness is based on this timestamp the pool agrees upon during consensus. The fourth important important improvement, our existing our BFT paper and also our many existing implementations, is that we have a concept of BLS signature, so that every node during consensus signs the current state, the current ledger and current state, and also multi-signature is calculated. And this is a very powerful thing which allows us to significantly reduce the read load to the pool. Because we can send read requests, and actually since the ledger is public permissioned, we expect much more read requests than write requests. So we can send read requests just to one node, not to the whole nodes, not to the whole pool, to every node in the pool. And also we can support a concept of observers, which can be used just for read requests. We can send a read request only to one node, and the client can get a state proof, meaning that the return data is really present in the returned state. And because we have BLS multi-signature, we have a proof that this state is really correct one, that it's not tampered by some malicious node. So state proofs plus BLS multi-signatures, only these two items combined can allow us to send a request just one node in the pool, which significantly reduces the load to the pool. Okay, also the Plenum has some non-important to be done items. So I'll talk about them later when we go to the three-phase commit section. So now let's consider briefly the workflow of how transaction is ordered. So transaction or write request is sent from the client to all the nodes in the pool. You can see this from client to all the nodes. And by the way, this diagram considers an example of 4 nodes and 1 client. Because 4 nodes is a minimum number of nodes that makes sense to have. The total number of nodes n is equal to 3f plus 1, where f is a maximum number of malicious nodes. Malicious nodes can be either just a node who's not available, shut down, or it can be a node which behaves maliciously. And this actually differs Byzantine fault tolerance from crash fault tolerance from CFT. So the node can be active, but it can, at some circumstances, behave maliciously or just degrade performance. Okay, so a write request is sent to all the nodes in the pool. Then the nodes, every node performs some static validation, some input validation to make sure that the request format is correct. And also they verify the signature, because for write requests, we require that it's signed by clients. After this, the request is propagated to every other node in the pool. You can see, so once a request is received by a node, every node is propagated to every other node in the pool. So we already have n square here. N is the number of the nodes, and you can see the number of propagates. It's n square. And the asymptotics, I mean, is n square. And once it's propagated to all the nodes, the client gets ARC. Like that request was acknowledged by the pool, and it's going to be ordered soon. If static validation didn't pass, then the client gets NAC with a description of why it's not passed. Okay, so once the propagation is done, the request is forwarded to all the replicas in the node. So what is well, it's not only when propagation is done, when we have a f+1 propagates from different nodes. So it means that when we have a quorum of propagates. So in this case, f+1 is equal to 2, because f is 1 for a pool of 4 nodes, so f+1 is 2. So what is replica? Specific of RBFT protocol and how it's different from PBFT is that it runs f+1 protocol instances or replicas. So every instance of the protocol is a PBFT protocol, where only the master instance, the first instance, is really responsible for ordering and applying requests. Actually, it's only the master instance who decides what is the order of requests on the ledger. And backup redundant instances are needed just to evaluate performance of master instance and trigger view change in case of degraded master. So this is just a mechanism to see if master behaves maliciously in terms of performance and do the view change. Well, from our point of view, it's well, way too much to trigger in this performance degradation, especially taking into account sovereign use cases where the ledger is permissioned, and we don't think that there will be a lot of stewards behaving like this, and even if there are, they can be just checked quite quickly by some public monitoring and so on. But in any case, this is how our RBFT works, and you can see that it's f+1. It requires f+1 more messages than any other PBFT-based protocol. So it's very chatty, and it requires much more resources in terms of CPU and memory. Okay, and here we have our to-be-done items. So the first to be done is that by RBFT protocol, every instance of the protocol, every of these f+1 instances, you can see every instance here is in this loop. It must be run in a separate process, leveraging multi-core architecture. So not only so if we have, for example, 8 instances, we need to have 8 cores. So that's why I was saying that RBFT requires quite a lot of resources. But the Plenum now is a single process application where every replica is run in the same process. And of course, it affects performance a lot. It affects how we trigger view changes. It may lead to some false positive view changes, and it's something that eventually must be fixed if we still want to go with RBFT, which is, from my point of view, questionable. As a second to be done item is in Plenum. You can remember this second item. Consensus is combined with validation and applying of transactions. What it means? It means that the master replica, which is responsible for real ordering of transactions, it has more work that needs to be done than any other replicas and as any other instance. You see that it needs to perform a validation of transactions, of every transaction in the batch. It needs to apply them and so on. But backup instances, they don't have any ledger attached to them. They don't have any ledger attached to them. They don't need to do this work. And it makes the instances doing uneven work. And it also can lead to false positive changes, because according to RBFT, it's assumed that all instances must be equal, must be totally equal. Only under this assumption we can really trigger the degradation of performance. So this is the second to be done. And well, as for the first one, it's clear how to do this. Just make the Plenum multi-process application. For the second to be done, it's rather conceptual, and it can be still a problem. Okay, so you can see that we have a loop. In this case, we have two protocol instances, and we have the same process on every protocol instance, on every replica. But the master instance, as I said, does more work, and this additional work is marked with blue color here. So these blue items are present only for master instance. So this is how master is different from backup instances. Now, also, please note that RBFT and PBFT requires that there is one leader, a primary node for on every instance. And in this example, it's assumed that node 1 is a primary for the first protocol instance, for the master instance. And every protocol instance should have a different primary. We omit it for simplicity, but in practice, it will be node 1 for first protocol instance and node 2, since we use round robin, for second protocol instance. So for the second instance, we'll have the same process, but this is the second node who's the primary and who's going to send preprepares. So now let's consider in more details how this process works. So the primary is responsible for creation of a next batch of requests. It can be just one request, or it can be a number of requests. How the primary decides that the new batch needs to be created? Actually, it goes for every ledger and see if a timeout happened, or we have a maximum number of requests which can be in one batch. As of now, usually a new 3PC batch is created either every second, or when we have, I think, 1,000 something requests. Also, please note that one 3PC batch may have requests only from one ledger, and of course, we are taking only the requests which are propagated, only the requests which are already propagated and forwarded to replicas. And by the way, our load test and our analysis and metrics show that although we have 3PC batches, propagation is one of the bottlenecks, because here we deal with the whole batch of requests, but here propagation still needs to be done for every request, and it's quite a heavy process as well. So the primary decides what requests and in what order needs to be included into the next 3PC batch. And for every batch in this exact order, Preprepare tries to apply them to the ledger and to the state. Before applying every other next request, it performs dynamic validation against already applied other requests, against uncommitted state. And if passed, it's really applied and it becomes a part of Preprepare. So you can see this is again part of what master does in addition to other replicas. So it performs this kind of dynamic validation and applying of requests. The validation is called dynamic because it takes into account the current state. So on this step, you can see that we did a static validation. It doesn't take into account the current state. So just some validation, like whether we have correct types for parameters, whether we have all required parameters for this request, and so on. But this validation, and it doesn't depend, the static validation doesn't depend on what is the current state. It doesn't depend on the order of transactions. doesn't depend on the order. But dynamic validation does depend on the order. That's why it can be done only when the request is applied. And just for example, creation of a new DID. So it can be done only by trust anchor, for example. But if transaction before this is blacklisting or demotion of trust anchor, so this person cannot add new names anymore, it will give you a reject that this new name cannot be added by someone who's not a trust anchor anymore. So you can see that order is really matters here. This is dynamic validation. So once doing all this work, preparing the 3PC batch and applying it to its state, the Preprepare sends a Preprepare message to all other nodes, And in particular, Preprepare contains the states, the hashes or root hashes of ledger and state, uncommitted, that is with applied requests, as well as requests itself. So I briefly mentioned that for ledger and state, we use Merkle trees. And Merkle tree is a very convenient structure which allows us to check the consistency of all set of data just by checking the hashes, root hashes. Because for Merkle tree, we just create a hash of every element, and then we create hashes for hashes, and so on to go up to the root. So we have these uncommitted states here. Then once Preprepare is received by every node applies this batch, these requests, exactly the same way as primary did before, exactly the same way, and in the same order. But it's very important because the order of requests is suggested by the primary. So if well, all the nodes have the same states, have the same code, the same rules, it should lead to the same state, uncommitted state on all other nodes as on the primary. And that's why we have this uncommitted states included into Preprepare. After applying this batch of requests, all other nodes performs verification. So in particular, it checks that the uncommitted states after applying these requests are the same as was on the primary. If some of this validation didn't pass, then we raise a suspicious code, the batch is rejected, and most probably view change will happen. In addition to checking that the data is consistent, by the way, important thing here, that this data is not committed yet. So it doesn't mean that it's in the ledger. And if a client will send a GET request, this data will not be returned because it's not yet ordered. It's just applied in uncommitted way. It's still being ordering. It's not yet in committed ledger, committed state. So in addition to these checks for consistency of data, every node also checks if the time is acceptable. So you remember this third difference that we also make timestamp as part of consensus. So this check is also done here. And also very important thing that Plenum protocol, consensus protocol assumes because we have this applying of requests in uncommitted way, we assume that every Preprepare needs to be applied sequentially. You can see that every Preprepare has unique identifier. This is vno Preprepare signo pair. And before applying this Preprepare, we check that there are no gaps, that this next Preprepare is really the next one. It can be applied. So it has a Preprepare signo different by 1 from the previous one. This is again just to keep the data consistent. If we didn't have this applying and validation of data, if we didn't have this uncommitted state, then of course we could process Preprepare regardless of whether they're sequential or not. But because of this, we need to apply them sequentially. By the way, it doesn't mean that we can order only one Preprepare, only one 3PC batch in a time. We can order multiple batches and on fly at the same time, but the Preprepare needs to be applied sequentially. If we have a gap, then the next Preprepares will be stashed and reapplied once we have a missing Preprepare. So again, we allow to have multiple 3PC batches on fly, but the application needs to be done sequentially. This is, by the way, how it's different from Tendermint protocol. Tendermint protocol, they allow only one batch fly. Okay, so if Preprepare is processed and verified successfully, then every node sends prepare to every other node. Every node sends prepare, and prepare just contains again the uncommitted state and the reference to this preprepare. Once preprepare is received, every node checks that it's correct, again by checking the uncommitted state, checking that data is consistent. And once a node has a quorum of prepares, and the quorum here is n minus f minus 1. Minus 1 just because we have preprepare. It sends a commit. Before sending commit, commit contains this BLS signature. BLS signature, this is, you remember the fourth important item here, that we have BLS multi-signature as part of consensus protocol. So every node signs the current state. Actually, what is signed? This ledger uncommitted state and state uncommitted, as well as some other metadata. This is what is signed. So we sign the current state in the tree, root hash. So every node signs this and sends the commit. And commit contains this BLS multi-signature. Once commit is received by a node, it's been verified that BLS signature is correct. And once we have a quorum of commits, and the quorum here is n minus f, this is 3 in this example. Every node calculates a BLS multi-signature. Actually, this is just a multiplication of every individual signatures. And this commit is, this batch is supposed to be ordered. The order message is returned to the node. So you can see that here we was in the loop for every replica, but now we returned to the node. And the batch is going to be executed on the node. This is done only for master instance, because for backup instances, we don't have any state, we don't have any data to be executed, but for master we have. And what execution done here is meant here, this is just committing the state. So previously we had the state uncommitted, but now we committed. We say that yes, we have a consensus, we have agreement that this batch, this order is correct. And the state becomes committed, and if a client now sends a read request requesting this data, this committed data will be returned. After this, we send a reply to every client. We send a reply to every client. Please note that in order to, the client needs to have a quorum of f plus 1 equal replies to make sure that the request was really ordered. Okay, so any questions about this diagram? I know that this is quite a lot of information, but maybe some high-level questions here.
So I guess one question I had, it kind of goes back a little bit earlier. When a node says that determines that he's the master, how does that happen? Is that just because master has its own a few behaviors that are limited to itself? So how does a node know its master? Is it configured? Is it when they all come up there, you go through a consensus and say, okay, this node is actually the master, the rest of us are not? How does that happen?
Every node has f plus 1 instances. The first instance is called master. The first instance is called master.
Oh, I see. Okay.
So you can show the maybe a better picture here. So you can see this is node 1, node. So we have 4 nodes, right? You can see the horizontal things is instance. This is a master instance. This is the instance of the protocol where we do ordering, real ordering, which will be written to the ledger. And the second horizontal line is where we do some kind of fake ordering. It's redundant backup ordering. So this is the same protocol. This one and this one. We follow the same protocol. And
okay.
so yeah, every node has two replicas. Replica for master protocol instance and for backup protocol instance. And what is marked here with blue, that this one, master protocol instance, has some additional work because it does real ordering. And this backup, it just doesn't do this. And you can see that every protocol has its own primary. So the same node cannot be a primary for multiple protocol instances. So for node 1, it's first node is a primary. For master instance, the first node is a primary. For backup instance, the second node is a primary. So the same process is done multiple times for every protocol instance at the same time, actually. So they all are done in parallel. As I said, it must be done in separate processes, but as of now, just in single process. But you know. Okay, so if no other question, you can have a look at this diagram by yourself. Just compare it with what's written here. And yeah, so another, I think, quite important diagram that I can show you is the sequence of requests. So let's consider the workflow of sending transaction, sending request to write from the both node and client points of view. I think it's both important for when you work with SDK and when you work with node. So let's start with the node side. So let's assume that node gets a write request from the client. So the node tries to parse the request to see if just something that the node understands. If not, the node sends NAC to the client. Then the node performs static validation according to some rules that, for example, this transaction must have this field required and this field required, something like this. Or, for example, that this field needs to be integer. If it's not passed, then NAC is sent to the client. The next part, thing that every node does, is signature verification. Again, if it not passes, then NAC is sent. Then it can be that the client just resent the same write request, which was already ordered, which is already in the ledger, and we actually check it. How we check it? Because the unique identifier of the request is a hash of its fields. So this is a digest of request. So it's a hash of all the content of request. And we have a special mapping, special cache mapping that this digest of request to the sequence number in the ledger. So the node checks if this request was already ordered, then it gets reply from the from the ledger, and immediately returns the reply. No need to order this request a second time. We can already answer the client. So if this request is not present in the ledger, when we start real ordering, so we go to the propagate phase. Here we send ACK to the client. You can see this green ACK. For the client, it means that yes, the request was successfully processed by the node and it's going to be ordered. So we need to wait a bit more. And the real ordering started. So this start ordering includes all the items from here. And during ordering, we perform dynamic validation. Dynamic validation, you can see here, when we apply CPC batch, we do this dynamic validation. And if dynamic validation not passed for this request, then we immediately send reject to the client. And we send reject, of course, with a message of what was incorrect. If the request is valid, then we finish ordering, commit it to the ledger, and send a reply. Send a reply. And the important thing here is that the client waits for f+1 equal answers. It can be either equal next or rejects or replies. This is how it works from the node point of view, from the client point of view. So the client sends write request, sends a transaction to every node in the pool, to all the nodes. Then the client sees. So if receives either NAC or reject or reply, and we have f+1 equal messages, then we just assume that we got a result, either successful reply or validation fails, NAC or reject. Also, there is a timeout. I think now it's about 60 seconds by default on SDK, but it can be overridden on SDK. What is exact timeout here? So if the client didn't get a request for this timeout, we just terminate. And by the way, if the client, I think there are two separate timeouts for ARC, for getting ARC and for getting reply. So if the client got ARC in, let's say, like 10 seconds, then there's a high probability that the request will be ordered. So this is what looks for the write requests. Then for the read requests. Again, we start from the node point of view. Because of BLS multi-signature and state proofs, the client can send read requests to just one node, not to all the nodes in the pool. So this node, which client sends a request, it's usually selected randomly. And once a node gets this read request, first of all, it tries to parse it to understand this request. If it cannot be parsed, then NAC is set. Then, if the type of this request is get transaction, the specific of get transaction is that we are trying to get a request by SIGNO, by sequence number in the ledger. So usually for read requests, we are we're doing a lookup in state and use a state proof. But for get transaction, we cannot do this, and we need to get it from the ledger because it's what we explicitly asked. So we get it from the ledger, send ARC, and then reply. And as of now, we don't have state proof support for get transaction. For get transaction request, we require consensus of f+1 equal replies. If it's not a get transaction, then we perform static validation, send NAC if it's unsuccessful. Then we send ACK to the client and get a reply from the state tree. Actually, what information we get from the state tree? We get the result itself, the real data, like what we requested. Also, we get a timestamp, and we get a state root hash. The node creates a state proof for this result and state root hash, and the state proof can be used that the result is really present in a tree with this state root hash. But of course, when client gets just state proof, it's not enough to just to believe this node, because the state proof state root hash can be incorrect, and that's why we also need BLS multi-signature. BLS multi-signature is created against this state root hash, and it proves that not only the result is present in the state, but the state itself is also correct, and it was agreed during consensus that this is correct. So BLS multi-signature is also returned. So with every reply to every read request, we have a result itself, we have a timestamp. Timestamp needs to be used for freshness, by the way. We have a state root hash, we have the state proof, and BLS multi-signature. So this is 5 main parts for every reply. Okay, so from the client point of view, how it looks like. So the client sends a read request to one node only. So if it gets a reply in X second, this can also be overridden. I think now it's about maybe 60 or 30 seconds. And by the way, one of the reasons you remember the slowness on STN recently was just because some of the nodes were shut down, and there was a probability that we will face these timeouts when sending read requests to one node only. So if we didn't get a reply in X seconds, then we resend it to another node. And if we asked all the nodes, then we also just cannot do anything and terminate. But if we got a reply during this timeout, then if this is NAC, then we go to this item. And if we have f+1 equal NACs, then we process result or the snack. it will mean that the read request is incorrect, so that we send some garbage. If we got reply, then we check if it has a BLS multi-signature and state proof. If it doesn't have, then we just wait for f+1 equal replies. This is the case for get transaction, for example. We don't have state proofs here, so we have to wait for f+1 equal replies. If we have them, then we check if BLS multi-signature is valid, and check if state proof is valid, check if the timestamp is fresh enough. Actually, that's up to application to decide. Or, well, in the scope of freshness epic, we will have some helper methods and some logic on SDK as well to help with proving this. And if all validation passed, then we claim that result is correct and we can process it on application level. So this is how it looks for read requests. So we have about 4 minutes. Let me just very quickly show you the storages diagram. So it lists all the databases, all the storages that we have, and it's about, well, I think about 18 now. Yeah, so it's about 18 storages. We use RocksDB. We use RocksDB for every of the storages because every storage is a key value storage. So the main family of the storages is ledgers. So as you know, we have domain ledger. For all application-specific transactions, we have pool ledger, which is used by clients and nodes to connect to each other. And we use config ledger for some configurations where we require consensus in the pool. Then every ledger consists of 3 storages. This is a storage for transaction log. This is just an ordered storage where the key is a sequence number and the value is transaction data, the transaction itself. And we have 2 storages for the Merkle tree. We have a separate storages for Merkle leaves and Merkle nodes. So this is for every ledger. We have 3 storages, two for Merkle tree and 1 for the transaction data itself. Then also we have state. For every ledger, we have a separate state. So we have pool state, domain state, and config state. Patricia Merkle tree is used under the hood. Yeah, key value is also used to represent Patricia Merkle tree. Also, we have some other auxiliary storages. For example, we have a storages for node status, for some data needed for consensus algorithms that we persist. We have a storage for BLS multi-signature. And this storage is used when client sends a read request, so the node can get the BLS multi-signature from here and send it back in the reply. We have a separate storages for attribute transaction, because in attribute transaction, we don't store the real content on the ledger, in the domain ledger. We store only the hash, and the real content is stored in a separate attribute storage, which is a mapping of this hash to real data. This is just for a trip transaction. And also we have a number of caches. So this is a hash so-called SIGNODB. So it's just a mapping of request to transaction sequence number in the ledger. So we can use it to check if a request, if a transaction is already ordered, is already present in the ledger. Also, we have identity cache. This is for efficient dealing with getting a verification key for DID. Well, the history of this is that previously it was assumed that the most popular transaction for the ledger is NIM and getting the verification key for the NIM. But it was before micro ledgers were invented. Now it's a bit different, but in any case, this cache is still used for some dynamic validation, for more efficient dynamic validation. And the last one is timestamp. It's used to get the state root hash for the given timestamp. So it allows us actually to get not only the current, the latest value, but also to get any value from the past. And it's in particular used in revocation, where we need to prove that the data, that the credential is not revoked at some time. Because usually we cannot require that it's not non-revoked just now, but we need to define what is the time. And because of how Patricia Merkle tree is organized, we can go to the past and get the data according to this timestamp. Okay, so we're out of time. Any questions about these diagrams or workflow in general? I know this is a lot of information, but yeah, at least this is some high-level inputs, and you can see, you can have a look at these diagrams in docs folders in Indy Plenum. Also, I suggest to have a look at the docs folders in Indy Node and read the README in both Plenum and Node.
That's actually good information. I'm glad that you went over that with us.
Yeah, thanks, Alex.
Thank you.